All right, so we're live. So welcome everybody. We are going to do our special guest today, and we're very excited to have Arthur Juliani. Arthur is a senior software engineer at Unity Technologies. You've been there for, it seems, for almost 2 years now, huh?
Yeah, that's right. It'll be 2 years in February.
Nice. And you've been studying, are you currently studying at the University of Oregon, the PhD?
So I'm technically on leave.
Okay, technically. Ooh.
Yeah.
But that's good. So you're actually studying cognitive neuroscience, which is very interesting. Yeah, so we're very excited to have you today because, you know, many of our students are actually, or say the big percentage of our students are professionals. They usually like work as a software engineer in companies and things like that. So this is a Georgia Tech program, right? I don't know if you're familiar with the Online Massive program, but a lot of the students that we get are just professionals that cannot just, you know, leave their full-time job to go to school, but they're really interested in you know, software engineering and machine learning and things like that. Our course is specifically reinforcement learning and decision making, and it's being taught by Charles Sisbill and Michael Liebman. And we basically, you know, well, us and a whole group of 10 other TAs sort of, you know, run the course every semester. So I'm pretty sure that our students are going to appreciate, you know, your insight as a you know, industry expert. And yeah, we're looking forward to hearing your answers.
Yeah, I'll do my best to provide as much insight as I can.
Yeah, absolutely. Alrighty, Chris, you want to get going?
Sure. Okay. So first question, tuning neural network learners, defining the size and shape of hidden layers, selecting values for alpha, gamma, etc. feels more art than science. Are there heuristics or patterns which can help select good starting points, or is it truly keep trying until your network fits the problem at hand?
So depending on the kind of problem, there are always some heuristics. I would say at the highest level, if we're talking about reinforcement learning in particular, data throughput is the biggest way to help in these scenarios. So if you have a small amount of data, there might be a lot of variance in that data, and it may be the case that you would have to kind of perfectly tune everything to extract the right signal out of it. That kind of changes as you go from collecting maybe hundreds of experiences to thousands of experiences or tens of thousands or millions. I'd be happy to kind of like, for any particular algorithm, dive into what are some good heuristics in terms of tuning this or that hyperparameter, I guess.
So how about we go a little bit into sort of the different kinds, because, you know, sort of like value-based methods are a little bit more sensitive to that, you know, hyperparameter tuning versus pulse-based. So can you talk a little bit about that?
Yeah, sure. So what you said is definitely true. In the case of kind of like deep reinforcement learning, it's often, at least in my own experience and a lot of what I've heard, that things like the DeepQ network or DDPG require more fine parameter tuning, whereas things that are the policy gradient class typically don't. This is because, in a sense, what these value-based methods are doing is somewhat harder. So in this case, they're both off-policy methods. So the hope is that you can learn some sort of meaningful piece of information from about your current policy from something that wasn't based on your current policy. And if that piece of information is wrong, or you extract the wrong, you kind of like extrapolate incorrectly from it, then you're going to be damaging your policy.
Cool. Which one is the sort of the algorithm that you find the most difficult to fine tune, or I mean, if you know, have one that you don't necessarily love?
Yeah, so the truth is, the DeepQ network, I imagine you've gone over that in your class, right? I think has been my least favorite. So it sometimes works really well for certain things, and then kind of inexplicably the same hyperparameters won't work well for something else. This is especially the case if you have a small amount of data that you're collecting from anything. One of the kind of factoids about the original DeepQ network paper is that the results that they post are kind of like the best out of multiple runs, right? So whereas typically what you might do is post the average out of 5 runs, say, and provide confidence intervals, what they showed were the very best out of 5 runs, which means, this one run works, but maybe the 4 runs, the average score was 0 or something like that. Yeah.
Fun.
Not so great. And I guess I would also say that that's kind of also been why there's been a tremendous amount of work getting the DeepQ network to be more stable and more performant. DeepMind, for example, have, every year they post 1 or 2 papers that have like, oh, here's how to make the DQN work better. It's actually somewhat similar for those who are familiar with like the generative adversarial networks. If you just take the original GAN paper and try to implement that on any sort of real image data set, you'll find that it doesn't work very well either. So these spawn kind of like little cottage industries around fixing the algorithm, so to speak.
Yeah, and so are you a little bit familiar with the TRPO and those, constrained policy optimization methods that are, a little bit more stable?
Yeah, definitely. So a lot of the work that I do at Unity, what I did when I joined is we started a code base around the proximal policy optimization, which is one of these constrained update methods that's a little simpler to implement and a little more straightforward than TRPO, but also turns out to often perform better anyway. Yeah, and the miraculous thing about that is that for many problems, the amount of hyperparameter tuning needed is much less because you can kind of have more fine-grained control over, for example, how adventurous, so to speak, your network is every time it doesn't update. So if you are willing to accept the fact that it may take a very long time, you can essentially ensure that your network is never going to have a policy collapse in the process of training.
We can say just like DQN, right? I mean, just the same thing. I'm kidding, obviously. Alrighty, let's go to the next question.
If I want to become an ML software engineer, what skills, tools, and languages do I need to focus on to be an effective engineer?
So I guess there are different pieces of it, right? So there's an ML software engineer, and I guess I would decompose that into the pieces of being a software engineer and then being a machine learning practitioner. So being a software engineer, there is all the typical CS work to have to understand. There's everything about understanding, designing, implementing, testing big systems, which is kind of independent of machine learning. And machine learning is, in some cases, very much just like an implementation detail rather than something unique there, right? Depending on what you're doing, the ML model can sometimes be just treated as a black box, and it has to be plugged into a system like any other. Then I would say the flip side, the machine learning side, I think what's most valuable, what I see when I'm looking to hire people at Unity and kind of like helping doing interviewing, is that people have implemented models themselves. People have read papers and implemented models. So what typically is kind of the case is a lot of people who want to get into machine learning or want to work as machine learning software engineers, they'll say, oh yeah, I downloaded this open source package and I ran it. I used this high level toolkit and I was able to put some data in and get some data out. And I think what that shows is that you can like read an API doc and use it, but not that you yourself have a deep understanding of machine learning. And I would say, that having like a PhD in mathematics or statistics is less valuable compared to literally just going through and doing the work of implementing these models in something like PyTorch or TensorFlow. Yeah.
This is the reason why we ask our students to implement the algorithms and not use any library. You see?
Yeah.
For example, you see the value of that? particularly the reinforcement learning, because reinforcement learning has so many caveats, right? So if you're implementing DQN, oops, sorry, I don't know where that came from. If you're implementing DQN, for example, let's say in PyTorch, you don't know if clipping the gradients is done here or there, or you may get confused between clipping the gradients and clipping the rewards, or there's so many layers to it that is so much better for you to just go do it hands-on, and then obviously it's not going to be perfect, but at least you get that experience.
Yeah, and there's especially with RL, a tremendous amount of intuition which kind of comes about from experimenting with different things. Especially if you have a system, or if in the process of experimenting, you're getting a lot of data out around what the policy is doing, what kinds of actions are being produced, how the reward is changing over time. Tweaking all of those things about it, everything has a meaningful impact, right? And understanding the relationship between what you change and how the outcome ends up is really, the secret to it.
Yeah, that's we have our project 3. There's a portion where students can write an environment or import it, and we always encourage them to write it because how you frame your problem helps get your intuition into, and you can play with the environment as much as you can play with the algorithm.
Yeah, well, especially because there's this piece which is kind of in between the environment and the algorithm, even though typically it sits on the environment side, which is the reward function. And misspecified or poorly specified reward functions are often just as problematic as having a bad learning algorithm, right? You could have the greatest implementation of whatever the state-of-the-art algorithm is, but if your reward function actually corresponds to the agent running around in circles, then that's all you're going to get at.
Alrighty, yeah, and the fun part, I think, is that sometimes it's not intuitive, right? Whenever you try to design a reward function, you really want to go this way, but it might actually confuse, just like a simple example, even the reward function plus gamma, for example, it makes a lot of a difference, right? Like in Sutton's book, I was surprised to read that the carpal example should have gamma 1 if you're going to have a -1 per time step, and you should have a discount, so gamma is less than 1, if you're going to have -1 on the end states, right? So if you fail states, not end states, but just fail states, which was very interesting because you can argue that that should be, why isn't gamma 0.9 or 99 when you're doing a -1 time step, right? It's just sort of confusing sometimes.
Yeah, definitely, and it's really just kind of like wrapping your head around a new way of thinking. So at Unity, we have these tools which people can use to turn their games into RL environments. And so a lot of people will post on our GitHub, and they'll kind of work through themselves how these rewards work. And it's often like kind of very somewhat amusing unintended behavior that can come about, right? So one of the ones that we like to use as an example is, say you have some floating platform that the agent can jump around. It can fall off the platform, which is bad, but it also has some goal that it needs to accomplish. But you also want it to accomplish the goal quickly, so you give it this tiny negative reward. Now, if you balance the tiny negative reward, or the tiny negative reward, with the negative reward for falling off, if those two aren't balanced correctly, the agent learns very early on that the safest thing to do is immediately jump off and kill itself, because then at least it doesn't incur the penalty of the episode going on and it getting these episodic penalties, right? So you have to, for example, make sure that it's always worse to fall off the platform and end the episode early than it is to continue to try to achieve the correct goal.
Yeah, I guess the one thing is very interesting. Sutton's book, he mentions, well, I mean, you have to do this, -1 if you want an agent to escape the maze, right? But you can get easily confused with, for example, the frozen lake environment. You don't want to do the -1 because the holes are going to be the holes of the frozen lake are going to be more tempting to jump than try to actually get all the way to the end. So in the frozen lake, it's actually 0, and it's only a +1 if you hit the goal. So many different little layers to it.
Yeah. You have to keep in mind that the reward function is really, the reward function decides the optimal policy, even if you don't know what it is, and it decides, it kind of creates the landscape of policies, the local optima and everything. You're deciding that shape with the reward that you create.
Yeah, exactly. Another one that people do that's might seem like a good idea at the beginning, but is ultimately not a good idea, is to reward intermediate progress. So, say you want some agent to navigate to a goal position, it's tempting to say, okay, well, if you only give +1 at the goal position, that's kind of a sparse reward. How about we give an agent a reward which corresponds to how close it is to the goal position, right? But if achieving the goal position ends the episode and what the agent's trying to do is maximize episodic reward, then what it's going to do is run around in circles and not touch the goal, because that's actually the best way to get the most reward, right? And amusingly, yeah, we have a number of people who end up implementing something like this and then wonder why their agent behaves so erratically.
Because the students just went through the reward shaping lesson, so it should be to feel familiar to them. Cool. Alrighty, next question.
What is your general process for solving an RL problem? For example, do you have a frequent go-to algorithm that you always apply at the start of solving a problem to get a feel for it before using more complex techniques?
Yeah, well, I would say, and I would recommend, obviously once people are no longer going through a class where it's important to implement things by themselves, I would recommend that, like, within the context of an actual real world task, to start with a very solid baseline implementation of something. So we at Unity have a baseline implementation of PPO, which we use as kind of the default starting place for everything. OpenAI has a great set of baselines called the baselines. Google Brain recently released a repository on GitHub called Dopamine, which has a number of great off-policy implementations. Yeah, I would say, like, pick one of those, find a state-of-the-art one, start there, and then pay very close attention to where it fails and why it fails. So in, kind of one of the immediate reasons is if you have control over the reward function, it could be that your reward function is misspecified, kind of like we mentioned before. I often see that the observations are misspecified. So sometimes the sufficient information for understanding the task or mapping the state to the action is not provided. So it may be the case that there are some very important variables in the problem that are just not being considered as potential observations. From there, it gets a little bit trickier in terms of your problem, because if you have what you believe is a well-structured reward function, sufficient observation statistics, and a state-of-the-art off-the-shelf RL algorithm doesn't work, then you get into this case where it could be the case that your problem is more difficult to solve. It becomes potentially a research problem, actually.
Yeah, I guess an additional thing to that would be creating the environments, and I guess you have a lot of experience in that, because I guess I didn't mention in the introduction that you're leading the ML agents repository, which is a framework with environments, right? So, okay, so students, well, but I did mention that in my Piazza post. Anyway, so I guess you have experience with this, but sometimes you actually create the environment in such a way that it's not Markovian. You don't have the agent is not capable of understanding what's really happening. For example, I don't know, you have an agent that I guess, well, I probably cannot give this example because it's from work. Another example. Anyway, so the stationarity thing is actually, I just lost it. Yes, the problems need to be stationary, and usually actually helps to just play your environment yourself as a human. And if you can tell, based on your interaction with the environment, how to play the game, then it's good. If you feel that you need more information, then there's an issue in there. But always you have to remember too the problem of memory, right? Like in the DQN example, you have a stack of frames or the recurrent cell, doing the same kind of thing, which humans we have that sort of built in, right?
Mm-hmm. Yeah, that's a great example. I was actually going to use kind of this example as a case where you might not have sufficient information, right? So if you build some sort of dodgeball game, right, where the agent has to dodge balls that are being thrown at it for some reason, you might be tempted, or one thing you might do is include in the observation the position of these balls. But in the case of dodging them, the velocity information might be extremely important to determining where the agent needs to be to not be hit, right? And if all you did was provide positional information and no means of extracting from that positional information velocity, then you can't expect the agent to learn to solve the task.
I guess there you go. That's a great example. I was like, how can I savage this? Actually, the carpal example is a pretty good one, and the lunar lander. The students actually implemented the lunar lander for project 2, and in there you have a continuous array, a vector with 4 variables, or I'm sorry, 4 variables is the carpal. This one is 6, 7, 8, with the velocities included. So if you wanted to, for example, move from the vector of continuous variables to images, you would have to stack them so that the agent can infer from the image the velocity and all these things.
Yeah, that's exactly right.
Very interesting.
And then I guess I would also say, one other thing to try, which is there's a lot of active research in terms of intrinsic rewards and exploration bonuses. And if you find that your problem has very sparse rewards, so it's mostly 0 and it's very infrequently something positive or negative, then I would kind of recommend looking into these exploration bonuses that can help augment the learning process.
And can you talk a little bit about the sort of similarities and differences between the exploration bonuses, which is this extrinsic reward or curiosity-driven agents, and this if you are familiar with the DDPG plus HER algorithm, Hindsight experiment replay, which is they're not the same, but they're kind of doing the similar things, right? They're giving a bonus to the exploration.
Yeah, so the HER algorithm is all about kind of like making the most of what you have. So in the traditional way in which DQN or DDPG is defined, your targets only ever correspond to actual rewards that are received. But in HER, you use a goal, and it's not about did you achieve an extrinsic reward, it's how well did your states end up corresponding to the goal position. And this is a nice little trick that can be done because then you can pretend that your goal was wherever you ended up, and you can give yourself a more robust signal. This is very nice. The only downside is that you have to be able to define these goals in some sort of space that's meaningfully comparable. So a lot of the work in robotics that uses HER, they can do things like, how far away was my robot arm from the object I was meant to pick up, or how far away did I push the object in comparison to its goal position, right? And so in this way, there's this very understandable space of goals. If it's a game, for example, it's much less clear what the goal space or state space looks like, right? So when we don't have a nice spatial representation for space, then it becomes a little bit trickier. And that's where things like these other forms of exploration bonus, like curiosity bonuses, come in handy. So in the case of these curiosity bonuses, the idea is that you provide the agent with some sort of reward based on a sense of novelty of the states that you end up in. And this novelty metric can be learned in various different kinds of ways.
Yeah, very interesting. All right, let's go to the next one.
Many of us are excited about introducing what we're learning to our professions. Do you have a favorite story for how a non-AI company put AI to work?
Well, I guess I can only talk about what most immediately comes to mind is the work that I'm doing at Unity. So I hope it's not kind of like too self-promotional, but to kind of give a little bit of context.
You can promote yourself all you want.
So it won't be myself, but what Unity does is they build this game engine, which is used by people for simulation, but it's also used by a whole lot of game developers, many of them smaller independent game developers, right? So tiny teams of people who want to build a game, who maybe don't have so many resources, but are passionate about building something. And what a lot of the work that we're doing on specifically around this ML agents tool is around allowing people to train agents that can be NPCs in their games. So they can be opponents or companions in their game or characters in the game. And so there have been a few indie game developers already over the past year who have kind of unprompted by us, picked up the open source software, gone through the process that everyone in this class is going through around setting up reward functions and fiddling with the algorithm to get it to work. But then ultimately getting characters in the game, agents in the game that do what they want and that are fun to play against. So there's this cool, really tiny indie game developer studio called What Up Games, and they're working on this little multiplayer game where a whole bunch of characters fight each other in an arena, and the AIs are controlled by learned RL models, neural net models. And this studio is, I think, 2 or 3 people, and there's no chance that they would have programmed an AI by hand to do this work. So it's really nice to see RL starting to be used by people who aren't RL experts, and to see it be used in ways that'll actually kind of like reach wider audiences.
So do you guys also open source this baseline that you mentioned? I mean, there's obviously a bunch of other libraries, but I guess you guys probably also have that code sort of built into the ML agents framework.
Yeah, exactly. So we ship kind of like these 2 Python packages. One is for interacting with Unity environments using a very similar to Gym API. We also have a Gym API on top of that, but we have kind of our own custom API. And then we have our own custom trainer that's proximal policy optimization that's kind of been handcrafted to work well with these Unity environments. And that's all open source. So the idea is that some game developer who really doesn't know anything about machine learning or very little can download these Python packages and kind of automatically have this way to do training in their games.
Great. Yeah, we actually we have a project 3 is about multi-agent reinforcement learning and a couple of different algorithms for that. And they have to build this, I guess Chris already mentioned, the soccer environment, but I know that you have an actual 3D soccer environment, which it looks pretty cool. So I think I'm going to propose the professors in the class, like, hey, can we actually use this one for next semester? It will be pretty interesting to have, students compete, basically, put their agents in there and then compete. But yeah, I haven't evaluated that, but it looks very, very interesting. All right, let's go to the next question.
What are some of the challenges in satisfying safety regulations, as well as the need of explainable AI to enable the use of online RL agents in potential real-life applications, such as self-driving cars?
So there was a lot to unpack there. What was maybe the first piece? I'll kind of go through them in order.
What are some of the challenges in satisfying safety regulations and laws, as well as the need of explainable AI?
I see. So there's, in the context of AV, safety regulations and laws, and then also explainable AI, right? So I'm not a legal expert, so I would say that it'd be difficult for me to say exactly what the legal challenges are around these tools. I can talk a little bit more about explainable AI and kind of see where that goes. So I would say at the highest level, this kind of ties into this field of AI safety, which a lot of people are interested in. and people are interested in it from different perspectives. So there's people who are focusing a lot on adversarial attacks, for example, which for those who are unfamiliar is the idea that you've trained some sort of machine learning model. It behaves somewhat like a person on whatever the task is, looking at images and detecting what's in an image, right? Understanding that an image of a cat is a cat. The problem is that these machine learning models can actually be exploited relatively easily in a lot of cases. So it's been demonstrated by changing as little as 1 pixel in an image. People have been able to change what a machine learning model classifies an image as. So you have an image of a cat, and a human would look at it and say it's a cat. You change 1 pixel, and now the machine learning model thinks it's an octopus or something like this. You could imagine in the case of a self-driving car or something like this, this could become potentially very problematic, right? Where you put a sticker on a stop sign and suddenly it runs the stop sign, right? So there's a whole field of work that's being done to attempt to train machine learning models that not only under normal circumstances behave like what you'd expect them to, but under a wide variety of different circumstances behave as you'd expect them to. And so this work, the explainability piece is kind of like one piece of this. So the bigger work is around having these models kind of be more generalizable, more robust. Then there's this explainable piece, which is maybe one of the ways that we can ensure that these models are actually more safe, is to force the model to tell us what it's thinking. So there's been some interesting work around, in the context of RL at least, where agents have been trained to, for example, not only output action choices, but output some sort of explanation for why they're making this choice. So I've seen this work, I don't remember who exactly did it, but I saw it in the context of Frogger, where they trained an RL agent to play Frogger. And then when the agent was, for example, the frog is on the road, all the different cars moving around. When the frog chooses to avoid a car, it would maybe go left, and then it would say, I went left because I don't want to get hit by the car, something like this. So this kind of forcing the models to explain themselves is very important. Now on the flip side, we can also, even if the model won't explain itself, there are a lot of people looking into ways in which we can better understand why models are giving the outputs that they are. It's kind of been, or it's often, the wisdom that's often repeated is that these neural networks are much less interpretable than traditional networks or traditional machine learning approaches or rule-based systems, right? So the thinking is that a rule-based system where someone wrote out all the rules is kind of the most interpretable. The problem is that's also the least flexible. So it's only applicable in a very small number of scenarios. Then you move up to kind of simple, shallow ML methods, where, for example, in something like a decision tree, you can understand why each branch in the decision tree was made. When you move up to a neural network, it's less immediately obvious, but there's a lot of work that's being done to understand why networks make the decisions that they do. So there's a lot of interesting work around saliency mapping. So in the case of having a image recognizing a machine learning model, that you give it a picture of a cat and it says cat. There's lots of very interesting work that forces the model to, for example, highlight what about the image made it say cat, and what about the image makes it think that it might be something else. And it's these kind of diagnostic tools that can be useful to say, oh, for some reason it thinks that this cloud is more likely to make it a horse or something like this. Maybe it's these kinds of tools that can lead to more robust models ultimately that are more likely to be safe.
Yeah, I guess one really nice paper on this particular topic, geared to reinforcement learning, is visualizing and understanding tire games, I think is called. And yeah, there's some visualization for the policy and the actor. So you have basically the saliency maps for both the policy and the actor, and on top of the Atari games. And it's very interesting because you can see how an untrained agent basically is, there are different levels to the research, which I thought it was phenomenal. One is you can see the untrained agent paying attention to sort of like the entire game frame, right? Versus a trained agent just paying attention to the ball and the bricks, right? But also very important is that they actually added an overfitting type of agent. So they train an agent and then hard-coded the actions, like illuminated pixels on top of the bricks to indicate basically what you should be doing. So I guess the one portion of explainability is not only are you doing the right things, but are you doing the right things for the right reasons, right? So the overfitting agent basically looks just at those 4 pixels, right? Going left, right, whatever, or I don't know how many pixels, versus an agent that has the overfitting in there, but they just randomize it. They make it part of the environment, just random, totally random, and the agent needs to learn to act in the environment. It's not paying attention to the 4 dots. That was a very, very interesting research. It ties, with what you said.
Yeah, that's a great point. And these saliency maps can then be used to do things like say, is the model making decisions for the same reason that humans would make decisions, right?
Cool. Alrighty, let's go to the next one.
All right. Neuroscientists are still studying biological brains and trying to understand how they work. What is the thing that we still don't fully understand about brains that, if understood, modeled, and implemented in RL agents, would have the biggest impact? That's
yeah.
ambitious.
I would. It's quite ambitious. I would say 2 things. They're kind of like at 2 different levels of the system. So there are certain things that neuroscientists understand really well, and I would say that machine learning practitioners understand really well as well. The biggest one is the visual system. So the human visual system, or all mammalian visual systems, are actually really, really well studied. The dynamics of them are really well understood. And the truth is that things like convolutional neural networks, like many multi-layer convolutional neural networks, actually exhibit a lot of the properties that we'd expect from the human visual system. And there's not so much more that's really needed to figure out there. I would say that the 2 pieces that really need to be figured out are, at the very lowest level, motivation. So human beings, or whatever you want to say, mammals, and things that have brains kind of like ours, there's no such thing as an extrinsic reward. Everything that motivates human behavior is always an intrinsic reward. It's a self-generated reward. And these rewards have kind of evolved over time to correspond to meaningful things within the environment. But there's no external force that's giving us a +1 when we do this, or a -1 when we do that, or anything like this. So the question is, the question of what's the best way to generate, in the context of machine learning models, these intrinsic rewards, which truly guide long-term interesting behavior, is still very, very unknown, right? So there's a lot of work around exploration and curiosity. But the truth is that there are a lot of other things that motivate human behavior besides just curiosity about the world, right? That's obviously not the only thing.
I wish Sutton was with us right now, because I think he would be like, what? But actually, we had a question similar when Sutton was with us, and this is my point. Like, I totally agree with what you're saying, and then Sutton is like, is that really the decision maker though? Is that really the portion that is taking the decision, or is the reward external to the core decision maker in you? And I was like, okay, you know what? You're a neuroscientist.
It's a question of what you call the agent, right? So if you call the agent the complete system, then the thing that generates the rewards needs to be part of the system as well. Because I think the truth is that a lot of people have started to demonstrate, like groups like OpenAI that spent a lot of money and resources training thousands of agents, all collecting data at once on all these machines with tons of GPUs. What they've demonstrated is that algorithms like PPO, if given enough data and enough computing resources, can optimize for any reward function. So then the more interesting question becomes, well, what's a good reward function to try to optimize for? Yeah, so that would kind of be my answer, which is in this RL formalism, we've actually gotten really good at this one piece in the middle, which is given something that we can model and given a reward function, we can optimize something for it. And the question is, what's worth optimizing that actually leads to interesting behavior? Then the other piece I would say is kind of more nebulous and maybe less related to RL than more to AI, whatever this is going to be, which is around concept learning. So the idea is, how do we learn reusable concepts that can be applied in different settings? So in most cases, you know, a lot of this work that's done around learning to play Atari games, for instance, all of these models learn to play one Atari game. But the truth is that many Atari games have what you might call similar concepts. So many Atari games have the avatar of the player that's in the game, have notions of jumping and moving around, have notions of items to be picked up. And these kind of correspond to, in our brains, high-level concepts that we then immediately can apply to new games. Currently existing RL methods and neural network models have no meaningful way of correlating those two things, right? So if the key looks like this in this game, the key looks like something else in another game, the filters that the convolutional net have learned have no way of correlating the two. You know, you may get lucky and they look similar enough, but if they behave in similar ways but don't look the same, then you know it's almost impossible to learn that correspondence. And I think there's still a lot of work to go to figure out how to do that.
Very cool, very interesting. So how do you relate this concept learning field with let's say we have, you know, transfer learning with one task and then you go to the next task, but you also have multitask learning, right? You learn multiple tasks at once. So can you talk a little bit about that?
Yeah, I think, you know, so I said that most people play Atari, you know, or most of the time it's one network per Atari game. There's started to be some work this year where if you have a really big network and a whole bunch of data, you can learn to play with that single network many Atari games. The question is, though, to what extent is just having a big network allowing you to memorize all 57 Atari games or whatever it is? Or how much are you actually taking knowledge in one Atari game and applying it to another Atari game? I mean, you could hypothetically, if you had a big enough network and you chopped it up in the right way, could solve any number of tasks, but that doesn't mean that you're generalizing in the same way that any sort of human would. Yeah.
Oh, go ahead. Go ahead. No. Go ahead. If you want.
No, that was it.
so one follow up though. I mean, because it's an interesting topic, I think, and you know, as much as you want to continue on this path, but there is another one now that you sort of mentioned this area about meta learning, right? So learning to learn. Can you mention a couple words about that? Or if you have experimented with it.
Yeah. I think meta learning is actually a really interesting area. It's been, so for those unfamiliar, the way meta learning has been explained to me, which was kind of when the light bulb went off in the context of RL, is that in supervised learning, you have the notion of a training set and a test set. And what you do is you train on your training set, but what you really care about is doing well in your test set. In the context of RL, a lot of people sometimes in the ML community make jokes about RL because RL researchers supposedly test on their training set, right? You have one game or one problem, one environment that you want to optimize the reward for, and you don't care about something else that might look different. In the context of reinforcement learning, meta learning kind of fixes this problem by instead of thinking about solving one task, one MDP, you start to think about distributions over MDPs. And the problem becomes, how can learning about some subset of tasks enable you to then very quickly learn about other tasks that are within the same wider distribution. So for example, if you train a locomotion-based agent to walk, and then you have some new kind of agent that has slightly different legs, it should be the case that if you've learned to walk on 50 different kinds of bodies, this 51st body should you should be very quickly either able to learn to walk or just simply know how to walk in this new kind of body. And that's what meta learning is about.
Awesome. It's fascinating. Let's see, we have 10 more minutes approximately. Well, a little bit more because we started a little late. 2 more minutes. So 50 more minutes. Let's see if we can score a couple questions, Chris. What'd you say?
Yeah.
Let's do it.
All right. So this question starts by citing the paper Evolution Strategies as a scalable alternative to RL. And have you and your team started using ES at Unity to compare ES versus RL firsthand? And does your work lead you to believe that ES is mature enough to replace RL, at least in certain fields?
Yeah, there's lots of debate around this. When that paper first came out, there was a lot of internal discussion we had around it. So for our work, one of the things that I mentioned we're very interested in is having small indie developers be able to use this technology. And the problem with the scalable ES paper is that you have to be able to run on 1,000 machines at once, which is not, so it's scalable, but that doesn't mean that it's easy to use or accessible to kind of like the lay person or the lay user. So we actually have not done very much of looking into it, kind of because of that reason. I'd also say that it's been inconclusive, at least from what I've seen, that these evolutionary strategy methods are really theoretically any more sound than the reinforcement learning approaches. So this kind of gets into some maybe more complex stuff about the kind of optimization landscape of reinforcement learning problems. And so, for those, I guess, who haven't thought of it in this way, you can think about any of these machine learning problems as you have some sort of like topography, and you want to either get to the lowest point or the highest point in the topography. And so what gradient descent-based methods like traditional supervised learning or gradient-based reinforcement learning does is you try to take these tiny steps from a single point to get to the bottom of the landscape. You minimize your loss, and then you maximize your reward. But what something like evolutionary strategy method does is instead of saying, okay, we'll have a single point and do our best to track the path to the bottom, those kind of methods are more kind of scattershot. So we'll place a whole bunch of points on the landscape and hope that they landed on good places. And if some of them landed on good places, then we'll put more around there and just keep going from there and try to get to the bottom. These methods, my argument, which is kind of somewhat opinion, is that these methods haven't been, so on the environments and benchmarks that show that they're competitive, I would argue that the optimization landscape is very simple. So for a lot of the Atari games and for a lot of these kind of like very simple locomotion tasks, you can randomly initialize your network and get a kind of good score. So, let's say some kind of game, you randomly initialize your network, and the best possible score is 1. You start off with 0.5. Now, you don't always start off with 0.5, but maybe 1/100th, 1 out of 100 times you start off getting 0.5. In this case, an evolutionary method makes a lot of sense because you try a bunch of things randomly. One of the random things you tried happened to be quite good, and then you're very close to the optimal solution. Now, I would argue that any non-trivial task, this actually isn't the case for. So if you think about something like image recognition, like there's the big ImageNet data set, all of these big high color images, and people train deep neural networks to do image classification. It's never going to be the case that 1 out of 100 times you're already classifying half the images right with a randomly initialized network. You're going to be classifying them right 1% of the time, no matter how many times you randomly initialize the network. And I think for most hard tasks that are going to be really impactful for the case of RL, it's going to be the same thing. You know, if you have an agent that you need to navigate some physically realistic environment, like some robot, right, that needs to perform search and rescue operations in the real world using a camera, right? It's never going to be the case that you randomly initialize a network and that agent knows how to navigate around debris and find people who might be in trouble, right? So in those cases, I think reinforcement learning approaches make a lot more sense. It could be the case that maybe if you scale up evolution even more, that it may still be useful. But these results, I think the problem is that the tasks we're trying them on are too simple to really be conclusive. There's a very long answer. I hope that was sufficient.
Can I throw in a question of my own?
Yeah, go for it. Absolutely.
So Arthur, you mentioned like indie developers and how you guys want to kind of optimize for the experience of the smaller shops and the layman. When do you see these developers kind of reaching for RL instead of like a generic kind of AI algorithm like A*, or whatever they're used to using for games? When is the jump that they make to reinforcement learning?
Yeah, it's an interesting question. It's something we think a lot about as well. And I think it's going to be a function. It's always a function of the developer, who they are, what kind of resources they have, right? So we think about like big AAA game studios, kind of the very top tier people who have 50-person AI engineering departments are probably going to very rarely consider an ML-based approach because they can always just engineer these big systems to solve the problems. There's also on the complete other end, the person that I'm kind of interested in is, someone who's more of an artist, a creative, a designer, a 3D modeler, who's putting together a game, knows enough programming to kind of like make the mechanics of the game work, but don't know enough to take that next step. I think the person like that knows enough to define a reward function, define some observations, and we want to get to the point that that's kind of like all they have to know to solve the problem. Now, you bring up this good point, which is that there's kind of someone in the middle. There are people in the middle who are used to using things like A*, simple planning algorithms, people who are used to using behavior trees to get behavior out. I think the argument there for these people is that machine learning, these RL-based solutions, can somehow provide more interesting behavior than what you get otherwise. So one example we have of this is in the context of locomotion. So we made a little game where we used RL to train a physics-based dog to fetch a stick. And so the dog, RL controls the limbs, and so the dog learns to kind of like walk around and get the stick and bring it back. Now, the way that this would be traditionally done is that an animator, well, there's the silly possibility, which is that you go into a motion capture studio and you motion capture a dog doing all these things, but it's probably not going to happen. What's probably going to happen is that some animator by hand crafts all of these animations for the dog, how the dog is going to walk, what they'll have to think beforehand, what are the scenarios. So if the dog falls over, maybe they'll put together an animation for the dog getting back up, these kinds of things. But there's only so many scenarios that the animator can think through or has the time to animate. But if you train an RL-based agent to do this, and in a physically based world, then whatever possibility can happen, if the agent's trying to maximize getting the stick, then it's going to learn to deal with every possible scenario. So what we found in this kind of case is we end up with an agent that has the equivalent of an infinite number of animations, because all it's doing is applying torques to joints. That is much kind of more lifelike and dynamic than what you get by just putting together some handcrafted animations. So I think this kind of this space is a really interesting space to explore, where can machine learning not just replace what you would have done before, but augment it in some sort of interesting way that gives you new kinds of experiences.
That kind of like infinite variability seems like something that the open world AAA titles might actually be interested in.
Yeah. There's, I would say within the context of the games industry, there's kind of two camps of people. So there's the first people, the first set, who are very excited about this because they're thinking about big open world games. They're already thinking about procedural, and this is a new way to have behavior in the characters in the games that's essentially procedural. That's dynamic and always changing. There's this other group of people though for whom they think about games as entirely scripted affairs, such that they want complete control over everything that happens. And the idea of a machine learning model is somewhat scary because the machine learning model is always kind of unpredictable, right? It ends up being similar to the case we were discussing before for the autonomous vehicle.
The explainable AI, right? Yeah.
Mm-hmm. Yeah.
Cool. I guess we have one more question.
Here's a Unity question.
Yay! Let's go.
Sure.
How do you design an environment to translate as seamlessly as possible to the real world? So training millions of iterations can be done more efficiently on a computer.
Yeah, and that's one of the big use cases that a lot of people are interested in. I would say there's two approaches to take, and both have value. So the first is you go for physical realism. So there's a lot of work that can be done to essentially get photorealistic graphics in a Unity world. This can be kind of expensive, especially if you have to hire a team of artists and designers to make this. The other approach, which I quite like a lot, is this notion of domain randomization. So the idea is that because you have a simulator, you can control all the properties of the simulator. And you're training some ML model, and what you really want it to be is very robust to different circumstances within the real world and without the real world. So there's actually some great work by OpenAI where they used Unity. Some people may have seen this. They trained an agent, this kind of like robot hand, to twirl around a cube so that the cube face, the face of the cube, is whatever was kind of designated as the goal. So they actually trained the vision part of that in Unity. And the reason they use Unity is because they could control all the parameters and vary them as much as possible. So they varied the lighting conditions, the color conditions, the shakiness of the camera, the shakiness of the hand, like a dozen other things. Like essentially any sort of property of the visual property, a physical property of the environment. There's interesting work where people vary the physics of simulations. So you have some robot that's supposed to do something, you train it in a simulator where the physics aren't fixed, but sometimes gravity is heavier, sometimes things are more slippery, sometimes things bounce off each other more, all these kinds of variations, such that when you finally put this model in the real world, it's actually been kind of battle tested against all these possible scenarios and is more robust to them.
Cool. Well, one last question in case that if you want to, make a plug, are you hiring? I mean, our students perhaps want to apply. I don't know if you are.
Yeah, it's true. We're hiring. Our team is looking for people of all different kinds of skill levels, both junior and more senior positions. So if you're interested in the kind of work I described, yeah, you're definitely welcome to.
Awesome. Well, and thank you so much for making a little bit of time. I know that you're pretty busy and you were traveling all this time, so we really appreciate you having 1 hour of your time to share your insights and have the discussion with the students.
Yeah, it's my pleasure. It's great. I love talking about this stuff.
Awesome. All right, so I'm gonna start the broadcast.
Okay.
Bye, guys.